Quantum material science has forever been a world of miracles and secrets. In this field, we are consistently confronted with odd peculiarities that resist our ordinary instinct. One of these weird peculiarities is called superradiance. It describes a synchronized group blaze of light from molecules that appears both captivating and secretive. While this effect has already been observed in extraordinarily designed research systems used by specialists for quite a while, superradiance in free space resembled an imperceptible ghost. If you like, superradiance is one of the most astonishing and astounding peculiarities in quantum optics. However, what does this term really mean? Well, to understand this, it's helpful to imagine the particle as a tiny receiving wire that can transmit light, or more exactly, an electromagnetic radiation field under specific circumstances. When we are done dealing with only one particle, but with an assortment of particles that are far separated and thermally energized, they emanate independently of one another. Therefore, the force of the radiated light is also proportional to the number of molecules. But in the case wherein the particles are extremely close to one another to build blocks, something astounding happens. In this situation, the nuclear radio wires begin to communicate with one another and, as a result, synchronize, making them radiate light whose force increases with the square of the number of particles. We can consider this peculiarity as the particles forming a single, giant radio wire that emits light far more effectively than individual, independent nuclear radio wires. This effect is generally referred to as superradiance. However, this nuclear display also comes with a significant limitation. In fact, superradiance has so far only been seen in optical resonators or optical cavities, which are special designs of mirrors intended to reflect light as often as possible to increase the electromagnetic field strength in principle. However, the resonant effect can also be produced by other parts, like lenses or specially created structures like waveguides or micro-rings. The primary function of an optical resonator is to trap and amplify light of specific frequencies. This, in turn, happens due to so-called resonance, in which, indeed, very specific frequencies interfere constructively after different reflections. For instance, they overlap and enhance each other and remain in the cavity accordingly. The light hence displays remarkable properties that impact its behavior. But if we now isolate ourselves from the specific research systems of the researchers, we recognize that superradiance has not yet been demonstrated in free space due to synchronization issues, well, until now. After all, specialists have now investigated this effect under different conditions with the help of theoretical simulations and have observed amazing differences between the two spatial frameworks. The fact that the particles in their scientific mirror cavity display aggregate radiation behavior is due to their interaction with photons, in other words, light particles, that bounce back and forth between the reflections of the optical resonator. This interaction, consequently, allows the particles to synchronize and transmit their photon emissions as one. And astonishingly, when stimulated by an external laser, the light absorption and aggregate emission of the particles can balance each other out, causing the system to subside into a steady state with a limited degree of excitation. The issue of synchronization in free space, however, arises when the laser energy exceeds a certain threshold. The system's behavior changes dramatically. The atoms in the ensemble can no longer radiate light quickly enough to keep up with the incoming laser energy, and they then transmit and absorb photons continuously without ever reaching a steady state. Well, at least on paper, although this transition to the steady state was theoretically predicted many years ago, it is still awaiting confirmation by experimental observation. But now, scientists from the Laboratoire SHF and the Institut Deutsch in Paris have undertaken the intriguing task of studying an assortment of particles in free space. Space that framed a lengthened, pencil-like cloud and conceivably went through the stage change of want. Anyway, the review results, once in a while, met with extraordinary disarray among different specialists. After all, it is interesting, no doubt, for iotas to synchronize in free space. Thus, it came about that the Colombian hypothetical physicist Ana Maria, along with a worldwide exploration group, put the outcomes under a magnifying glass in the course of additional examinations. In doing so, she brought a surprising truth to light. the specialists really viewed that as molecules can, to some degree, synchronize their discharges in free space, which, in turn, suggests that the previous free space trial didn't decisively notice the very brilliant stage progress exhaustively. The new recreations had the option to imitate the exploratory data, furthermore, to make sense of why complete synchronization couldn't occur under the given conditions. However, maybe, and this is the invigorating part, the stage change could happen under different circumstances and at higher densities. Albeit, as per Ray, we would then enter a domain in which our hypothetical strategies come up short. Furthermore, a genuine quantum portrayal is required. Rather, on a fundamental level, the arrangement of complex issues requires the combined endeavors of hypothetical and test physicists. While the scholars foresee how frameworks ought to act in their numerical models and recreations, the common-sense specialists put these forecasts to the test with experiments. As such, this is the ticket, the bridge between conceptual thoughts and real-world, recognizable peculiarities is constructed. One of the greatest inquiries in such a manner is whether it's feasible to create entangled states in various nuclear frameworks in an optical depression. This is conceivable due to the one-to-one cooperation of the iotas. But how this works out in free space is still to be explained. This is to be expected, considering that a whole framework can be finely tuned to put the molecules in the ideal quantum states, while it's in the nature of things that free space systems are significantly less easy to control. On the one hand, there is the issue of the frequency induced by the interaction, and not least the way that the outflows here happen in every single imaginable bearing, also not primarily in the optical sea. The recreation of free space, so one would expect that these variables would change the material physics of the framework. Yet, shockingly, Ray's group found that the fact of the matter is very different. To unwind the background, the scientists performed a progression of hypothetical reenactments with a model in which each molecule was viewed as a dipole that retains and radiates both the photons from the laser and the light transmitted by the other particle. ATS subject matter authorities agree this was all the more difficult, since the quantity of states in the whole increases linearly, while in free space it can increase dramatically with the size of the framework. Eventually, the specialists used their model to investigate the properties of the whole nuclear cloud. The laser beam went about as a smooth wave that forced a particular stage design on the molecules, in this manner controlling how they collaborated with one another. Precisely how these variables impacted the conduct of the framework was thus recreated in light of different conditions, including different laser powers and nuclear densities. As indicated by Ray, the reproduction showed that a purported mean field estimate, which extraordinarily decreases the intricacy by regarding the iotas as traditional magnets, is adequate to replicate the physics. Anyway, to guarantee consistent outcomes, the model was then validated using more complex methodologies, and ultimately, the researchers found that although the free space test was consistent with the depression model, the two systems acted differently within a limited scope of laser powers and nuclear densities. This is because when the laser power increased over a certain limit, the aggregate effects in free space that led to superbrilliance in the optical depression vanished. The particles appeared less as a coordinated group and more as independent radiators. Anyway, the researchers emphasize that their outcomes open up totally new roads of exploration in quantum physics and, indeed, highlight the significance of coordinated effort between experimental and theoretical specialists. Anyway, the reality that the universe of superradiance still has some mysteries in store is shown by the series of investigations led by Faro Marar from the College of Innsbruck. A few months ago, he published in the journal Physical Review Letters. The hypothetical physicist had considered two assortments of particles in a pit to investigate how these two nuclear troops can simultaneously produce light. In this regard, there are fundamentally two possible outcomes. Either the two aggregate nuclear receiving antennas complement each other to form a single, very large receiving antenna that radiates light much more efficiently, or the systems rival each other in a damaging manner, eventually suppressing the very brilliant light emission. The latter happens particularly when the two assortments have the same number of molecules. However, Marar additionally tracked down cases in which the two large antennas produce light that encapsulates a superposition of the two kinds and shows a swaying character. And this time, too, The hypothetical forecasts are to be tested in current cavity tests, and the outcomes could be used in a new generation of so-called superbright lasers. And now, you're free to tap on the subscribe button, press approval, and subscribe now so you won't ever miss a new video from us again. We'll see you soon.